All right, and now the last thing is the deep learning. So let's go over this and then we're going to start with the hands-on. Let's quickly look at the deep learning. So this is an extension of the neural nets that we saw a little bit earlier. Alright, so if you want to know what the difference between neural nets and deep learning, just read some of that on the top here. So you see these characters, you guys? It hasn't finished rendering the HTML on the fly. This is just latex code. It's gonna fix itself once it's done with the rendering. So never mind these things. So I know it's kind of difficult to look at this thing, but let's just go down to here is again some examples of the most commonly used activation functions. So these can be specified at runtime by the user. And here's a schematic of what's happening. Again, the input layers, hidden layers in between in gray, and the output layer or layers in green. By the way, if you look at the code, the R Markdown code of this, you can see exactly how this graph is generated. Oftentimes you may have to generate graphs like this. This is not an image. This is a, well, it looks like an image, but it's actually a graph that's rendered into the HTML page. Oh my gosh, how long is this? Oh, because there's some heavy images here, I guess. That's why it's a bit difficult. Anyways, the activation functions, let's not worry about them. Here's the biological relevance that I told you about, how, you know, here's the big brain. If you keep zooming in, a bigger network, when you get to the single neuronal cells, it's got dendrites feeding in inputs from other neurons, and it's got axons feeding stuff out for the output. So here is your perceptron, is the neuronal equivalence in the machine learning. It gets the inputs, weights them, W1, W2, W3 by their weights, weight averages them. It perhaps adds up this constant term, which can be a negative thing, to temper down the activation. These are all parameters that get estimated from the data. It applies the activation function, and then at the same time, these things kind of either fire or not. So it generates an output. And just to give you an idea, let's just work out a couple of examples. The first one is the XOR operator, the negative OR. Here is what it does. It got two inputs, they're all binary, 0 and 1. 4 combinations, 0, 0 leads to 0. So it's the OR negation operator. So if it was the OR operation, it would be wait. That's right. It's OR but not both. Okay? So 0 and 0 is 0, 1 and 1 is 0 because they're both 1s. And then the only time that it generates a 1 as an output is when one of them precisely is equal to 1. So let's look at this very simple neural net. It's fully connected. Everything connects to everything else. You have the X and Y. The weights are going to be 1. The weights are indicated on the connecting lines. And then I've labeled these hidden nodes in the hidden layer as hidden layer 1 node 3, hidden layer 1, node 2, hidden layer 1, node 1, and then the thresholds, remember this activation function has a threshold here, the thresholds that they have to bypass to fire a 1 are indicated right after the TH, threshold 1, threshold 2, threshold 1. So let's just work out some of these things to see how this thing works. If I feed in 0 and a 0, 0 gets fed in here, it does not pass the threshold of 1, so this, the first one fires up a 0. Is everybody here with me? The second one, if I feed in 0 and 0, gets 2 zeros, weighted, equally weighted. It doesn't reach threshold 2, okay? So it does not fire, fires up a 0. And the same thing over here, so Z is 0, so the output is 0. Let's take one of the situations where 1 is 1 and the other one is 0. Suppose Y is 1 and X is 0. If Y is 1, it meets the threshold 1, so 1 is sent to Z. You have a threshold of 2, you received only 1, so it outputs a 0. And the last one outputs a 0 again because X is 0. So you get a single 1, and therefore the output is 1, just like you expect it to be, right up here, for a 0 and a 1. And if both are 1, you guys, this thing here is going to generate, it's going to pass the threshold, so it's going to send a 1, but its weight is -2. So the 2's that come from the top and the bottom are negated by the middle, and that's why it outputs a 0. Does everybody see that? So the same thing can be done, and I kind of worked out all the details here if you want to look at. The next one is NAND, not an AND, which kind of gives you 1 everywhere except when they're both a 1. Pretty much the same thing, except that you have a threshold of 1.3 that you need to exceed. And 1.3 is not important, it could have been 1.5. It needs to be a number between 0 and 1 to output what you need. And the weights, however, of these guys are -1. And again, these neural nets, they're not learned. These are human constructed, is what I'm saying. Is that right here with me? Because we force the weights. There is no learning here. A human set in and we just give them the weights. But in reality, these weights are computed on the fly. And so are the thresholds, these B's that I had at the end when we did the...
Question?
Yeah.
I have a very fundamental question. So how can we differentiate an ANN with a deep learning network? Or how can we say when does an ANN becomes a deep learning neural network?
Oh, the deep neural network simply refers to a standard neural net that has typically many, many layers in the dozens.
How many?
Well.
After how many layers does he say it's a deep?
Well, I mean, it's one of those things, okay? Neural nets have been known since the 80s. The reason why they became popular in the past 5 years, let's say, as deep neural nets, is that the computational abilities increased to the point where we can go really deep. Something that was not, computational complexity increases exponentially with every layer. Is that right? We add an extra layer, an order of magnitude more complex. So people are not able to do that, but lately people are going to 70, 80 layers with maybe hundreds of nodes. It gets getting complicated, but it's still far away from the human brain has, 13 billion neurons. Multiple networks and whatnot. So, how many and when does deep start versus non-deep? Well, it's more of a art than science to some extent. Anyways, so this is a good example, but let me just skip over this. You guys can look at it later. It classifies, it's an interesting example, but let's just skip over it just to get to the interesting stuff. Computational graph, okay. some plots. Okay, something about the invocation protocol. We can read these later. Okay, so let's look at some case studies. The first one is AOS, the very same AOS data that we looked at before. Column 7 is the clinical output diagnosis. Again, we're going to have our 70-30 split into training and testing data. Here is where we're going to define and the output layers, and this is just a single layer thing that we create. And right up here is where we fit in the feed-forward neural net model, and you can specify either GPU or CPU computing, number of rounds. There's a lot of specifications that can be, they have very strong effect on the results. You're not going to believe it. So you have to try it with different parameters to see how it works. Then you call the predict function, just like we did before, and report root mean squares, etc. The imaging is where, okay, so there is a IBS, Irritable Bowel Syndrome data as well, classified again, not too good of an accuracy, so 60% accuracy, marginal. And the reason why this happens is, look what's going on here, you guys. The testing labels, the testing data labels, IBS or control patients, is so evenly distributed across the spectrum of the probabilities generated by the neural net. And now this doesn't mean that neural net failed. It simply means that my model setting of the neural net failed. Maybe I didn't use enough layers, maybe I didn't use the right thresholds, maybe I didn't use the number of iterations. There's a lot of things that can be manipulated here. I'm sure this model can be improved. But in the current model, there is no way to get a better approximation, because remember, I have to dichotomize, and no matter where I cut this and declare these guys controls and these guys IBS, the green and the red are so intermixed that they're untangable. I cannot untangle them separately. So 60%, well, 60% it is. Quality of life ranking, there is another data set. The results here are a little bit better. Notice how the two classes actually are pretty well divided in this case. And I am getting almost the perfect testing confusion matrix. Only 2 subjects were misclassified. One was here and one was over there. So 97% accuracy, that's not too bad. The handwritten digits, we saw these. Oh, we haven't seen these before. So this is for digits. If you're interested in, look at this thing. It's a beautiful example because it has how many thousands? $20,000, I believe. 28,000 manually written digits, and you're trying to classify them. So the data is large. You know, you can download it and zip it. It kind of shows you how this thing works. Separate them, training, testing. Here is what one of these images looks like. That's the number 2, obviously. Now in this case, the difference between and the OCR that we talked about earlier is that for the character recognition, we used derived measures of what's the extent, where it's located, and various curvature measures and whatnot. Here we're actually processing the raw images, not derived imaging metrics, okay? So we could have done the same thing as well, but it's more interesting because we're interested in broad brain images to look at these. So I'm just showing you how to reconstruct these, how to render them and all that business. And then we're going to look into the, so 9 with a dot instead of a 6. So here is the probability table that kind of tells you approximately what proportion of the 10 digits were present. And they're about, 10% or so of all classes. Configure the neural net, train on the CPU, define the model, and now look at the reported training data accuracy at every iteration. Starts at 86%, goes to 95, 97. Sometimes you can see drop actually of the training accuracy, and it may go back up. It figures out that it's going the wrong way, reverses course. Eventually it should converge to something reasonable. In this case, you see, it almost has a perfect training accuracy after 10 rounds. Now for the forecasting, we are going to use the test data to predict, and here is the predicted labels. Okay, you see they're kind of equidistributed roughly. The question is, in this specific case, the data does not include labels for the testing data. We only have the images. So there is no way for you to compute the accuracy of the neural net on the testing data because you simply don't have the labels. However, I simply went ahead and printed something about you see, the corresponding proportions, if you want, of how often was 0 and a 1 present. So this kind of gives you, if you're in the bulk part correct, the proportions of 0s and 1s and 2s in the training is going to be the same as in the testing, and the predicted proportions are right up here, so we can kind of argue that these are good or bad. And then I went ahead and plotted for all of these the corresponding, let's see, plot the relative frequencies between the number of the training data labels against the testing data predicted labels. Okay, so these are not directly associated unless testing and training data are proportional, and you can see that they're roughly speaking they're roughly speaking linear, which kind of suggests perhaps that we may be doing okay. And then I decided to plot the 10 of these things, or I don't know how many are there, maybe 8, just to print the corresponding image label and the actual images and the corresponding labels. So you can specify here where to start and where to end. In other words, how many images you want to pair with their corresponding labels. So this 0 image was classified as a 9, incorrectly obviously. The 3 was correct, 7 was correct, 0 was right, 3 was right. So the first 7 that we plotted, the deep learning classifications are mostly accurate with the exception of this 9 here. You can print them all, and here is a there is another table. So let's just skip over. So because in this case we didn't really have the testing, the validation data labels, it's a bit difficult to assess. The final thing that I want to do is just show you one imaging example that's very appropriate for us, classifying real world images. Now, I want you to think about it with the perspective of brain images here, but not only two-dimensional, but three-dimensional. They can be done exactly the same way with 2 very important caveats. Caveat number 1 is that three-dimensional objects take exponentially longer to compute, okay? And these calculations, they take maybe a minute or so. We're still in the process of making them reasonably efficient to do them in 3D. They're not perfectly it's not perfectly working yet because lots of complexities. But for two-dimensional images, it works beautifully. It's really well done. The training was done by the folks that developed the MXNet package, the LANET protocol. So we are going to be preloading the train model. Okay, here is the inception zip file. It's a large zip file. And then you essentially, you need the imager package just like we had before to be able to parse in and out PNGs, JPEGs, GIFs, and other images. And then you go ahead and one at a time load an image. So that's a weather map of the US. Kind of random image. It doesn't really matter what it is. The first thing in the protocol is to go ahead and pre-process the image. So we're going to define this function that kind of makes these images, roughly speaking, homologous. Remember, I've told you about it. If things are not homologous, it's difficult to interpret them succinctly in the same protocol. So this would include reshaping the image, making them, roughly speaking, square, resizing, maybe manipulating the intensities a little bit and whatnot. So that's a very different image, as you can see. But roughly speaking, it resembles the characteristics. First of all, it was trimmed on the side, which is not a good idea, but that's what it happens. And then what you want to do is you essentially, remember, we're skipping the training program here because training for images is very hard. Imagine a human needs to label an image with whatever is appropriate, diagnosis, clinical assessment, whatever. And then these things need to be paired. You need to learn on thousands of these things. It's a very expensive process. So we're using something that, for our images, we're using something that people have pre-trained on many thousands of labeled images. And we're just calling the predict method here, providing the image learning model that comes up, and then simply the normalized, which is spatially and intensity normalized image, print the dimensions of this prediction, and then you go ahead and right up here. So you're going to order the results of the probability in terms of decreasing order. The highest probability labels that are associated with every image are going to be on the top, and as you go down the list, the probabilities are going to be decreasing. So these are the indices, you guys. These are the indices of the labels that are most likely associated with this image. Now, we don't know what these labels are. We got to look them up, and that's what we're going to do. But these are the indices in the rank order fashion. And again, I just want to make sure everybody understands. You're not ranking these values. These are just indices of the highest probability labels that are associated with that specific image that we predicted the class of. Is everybody here with me? Now, what do these things correspond to? Well, you can load in the corresponding text labels of these images, and then you simply transform each of these. So the first label, 855, corresponds to this one here, which corresponds to theater curtain, it says. The second class says fountain, commander, greenhouse, but look at their probabilities. The probabilities are very, very low. So in other words, and even the top classification label has a very low probability. This kind of tells you that this is an image that cannot be well classified. We don't have enough info. Humans cannot even classify many images. We are very, evolutionarily trained to recognize faces and whatnot, but we're not too good with images in general, right? So the algorithm here says, I'll report the top 10, but none of them is actually good. So in this case, you would say unclassifiable. The next image is this one right up here, and I've provided references for all of these. These are all Creative Commons licensed images. So, a nice lake, would appear here. Once it's normalized, you call the predict method, And then what it reports for you is breakwater, dock, lakeside. The corresponding probability is 65%, 20%, not too bad, and 12%. So these are all relevant labels, right? Does everybody see that? So the next image, a beach. So scaled version, send it to the classifier. It says sandbar, lakeside, seashore, right on the money in a way. So very well classified. Volcano image, okay. The same thing, it hits it right up here, volcano 99, okay, so that's almost good. So this image, I don't know, it might have been part of the training, but remember, we don't have the training images here, we just put in testing images. Geyser, well, yeah, volcano is a type of geyser. Alps, well. And now here's the brain surface. Now look at this. Obviously, brain images are strange, right? This is not a brain image, it's a cortical surface reconstruction snapshot of. So it classifies it as a brain coral. It obviously doesn't know any brains, but it says a brain coral, 50% likelihood. The next one is a mushroom. Yeah, it is mushroomy. And various other things with lower probability. Not too bad for this one. Here's a face mask, synthetic image. This one is correctly classified as a mask, 37, 38%. Ski mask could be. Analog clock, not really. So imagine what's happening here, right? Okay? If you have sufficient amount of radiologically labeled brain scans, and when I say sufficient amount, I mean thousands of scans with verbose description of what the physician or the radiologist has labeled these scans. Tumors, trauma, hyper intensity, myelination, whatever. If you have this database, it's not hard to train a deep neural net algorithm, save the model out, a new image comes in, and when I say image, I mean either two-dimensional images or three-dimensional volumes. A new image comes in, you pipe it through, and it gives you a diagnosis. Right? Does everybody see that? So that's why I wanted to finish with this example here. We don't have this working yet for 3D, again, as I said, because of lots of complexities, but we do have a lot of metadata for thousands of subjects, close to 10,000 subjects. We have a lot of metadata, certainly their diagnosis, certainly cognitive scores, ages, genders, and everything else that goes with demographics. So we're thinking about training on these and outputting not really a clinical diagnosis, but a feature of interest that you specify. You want to know, okay, look at this brain and tell me approximately how old is this subject. That is an answerable question in this setting. Okay? We don't have the tools yet, but the machine is there. It's just not trained to work on these things yet. Yeah?
Can you please explain again how are we calculating this probability?
The probability here is computed by, in the neural net example, so it goes through the deep net with the learning has already happened. So what it does is it pipes just like we did. Remember the XNOR functionality. We just feed in and we simply record the result. Now their results are based on these numerical. Remember I showed you the result 857. So they're labels, but these labels are paired with textual descriptions, okay? And the probability is a representation of how, I guess, not consistent, but how confident is the learner that this is the right label. Because see what happened in the first case, remember, when the best probability was 9% or something like this. It was just confused. There were too many possible candidates. And remember, it actually assigns, the way it works is it assigns probability for every possible outcome. They total to 1. Now, when you get a dilution, when the things dilutes into many, it just knows that it's not very accurate. It's just too dispersed. The energy is dispersed. But on the volcano, it was very concentrated. It hit it right on. So the probability is just the distribution that the image gets assigned to every of the labels.
So, yes, so why...
And you rank order these.
What?
And you rank order the probabilities once you label.
So while it calculates like the probability density function, it calculates, this probability values, right?
Yeah. Why, say it again. Why?
While it calculates the probability density function.
It calculates the probability density function of all possible outcomes it knows about. Yeah.
Okay.
And then we rank order these, and we simply report the top 10.
Okay. So this can be calculated. This can be calculated in R for each image.
Yeah, absolutely. I mean, this is what happens here. You can actually run this code right now and get it to work. Again, I mean, you have to draw the line somewhere. If something is less than, if the highest probability assignment is less than 20%, it's probably too new to be accurately predicted.